our series on momentum. We're in the third lesson. We've done a lot already. We're starting to get to the nitty-gritty, which is really nice, and it's lots and very exciting. So, this is the prevailing thought for this lesson. What do people mean when they say something has gained or lost momentum? Because we hear that often. They'll go, the golf ball gained momentum as it rolled down the hill. Or the cyclist was going up a hill and they lost momentum, which is why it's really difficult to cycle uphill. Or sometimes we even do it in terms of work or in terms of they gained momentum in getting something done. So we speak about it, but what does it mean in terms of science? What's the nitty-gritty behind that, okay? So that's what we're going to look at today. By now, you should know the definition, the equation, the properties, and how Newton's laws affects it. So today, we're going to look at, we'll go back there quickly, change in momentum. That's what we're focusing on. There are some key words that we need to get. Number one, initial momentum. What do we mean by initial? What does initial mean? Okay, we know what momentum means. We're going to look at final momentum. What does the word final mean? Where does it come into play? Okay? And then change in momentum. How the object's momentum changes is actually really important for us. Okay? Let's break change in momentum down. So change in momentum, first of all, is a vector. Momentum is a vector, so change in momentum is a vector, because when we change momentum, it's not a new concept, it's not a new quantity, we're just looking at how it differs, whether it gets bigger or smaller, did we change direction, all of those sort of things, because how momentum changes affects the motion of our object, okay? Because it's a vector, before we get there, sorry, for momentum to change, velocity changes. We have spoken about in the past, when we did Newton's second law, that it's possible for the mass to change. Absolutely. But we're not going to consider that in our study of momentum, okay? So we're going to consider what happens when the velocity changes, okay? When velocity changes, it's a vector that's changing. Because it's a vector, it has a direction. That direction is the same as the net force. This is what we have to keep in our minds. Momentum is a vector. The direction of momentum is the same as the velocity. When the velocity changes, there's acceleration. The direction of the acceleration is the same as the net force. That net force causes the change in momentum. That change in momentum has the same direction as the net force. It's all about the net force here. So change in momentum is related to acceleration. We've got to think about this one carefully when we look at the direction of the change in momentum, because an object might not change its physical direction. So in other words, I could have something going forward, but the change in momentum is backwards, and that happens when it slows down, okay? We're also going to consider what happens when an object changes direction completely. Then where's the change in momentum? And here, using our negatives, when we look at it, because we're dealing with vectors, becomes very important. So we've got to keep our head on straight when it comes to direction, okay? So, we have thought about this. We've done this. What happens when a net force is applied to an object? There's several things. You've done net force on objects lots over the years, okay? You would have done it in lots of places other than in your senior years as physical science. So a net force can do lots of things. It can change the velocity, it can change the acceleration, it can start and stop objects moving. But essentially, the big thing for us is when a net force acts on an object, the object's going to change its velocity. So that's important, but let me just remind you again, okay? So, a force can do this. It can start an object moving. So if it had zero velocity and it starts moving, its momentum is going to have changed because the net force is causing the velocity to change. It can start and make an object speed up, so it's already moving, it gets faster, slow down, like driving in a car and putting the brakes on, or it can make an object stop. All of those things involve a change in velocity from a net force, okay? It can cause an object to change direction. We all know that, like when we turn a corner. We're not going to consider a change in direction at 90 degrees when it comes to momentum, but a change in direction definitely changes momentum. And we're really going to talk about change in direction when something hits a wall and bounces back or hits a floor and bounces up. We're not going to do anything that's two-dimensional, so it goes off at angles. Okay, we're not doing that. We're going to make it simple. An object can change its shape. Now, if we change its shape, it doesn't change its momentum. Okay, it's like playing with Play-Doh when you were little, and you squish it and squash it and all those sort of things, okay? That doesn't affect momentum. We can also cause it to rotate, spin, go in circles. That has nothing to do with the momentum we're working with, okay? You do get rotational momentum, but we don't do that at school. Study physics when you get to varsity, hopefully some of you will, and you'll do it there, okay? So here, that's not something that's within our scheme of what we're doing. So the three that is important are those ones, okay? Let's go back here, is the fact that all three of these things involve the vector changing, okay? So a change in direction changes the vector. And in fact, when you change the direction of motion, you actually have technically caused acceleration to happen because you've changed the direction of a vector. That means the vector's changed. Makes sense? And all the first two involve a change in velocity, which must change the momentum. They go together. All right, so change in momentum is a vector. And this is the one where it starts to get a little hazy, okay? It has to have direction. How do we determine the direction? We're going to go back to Newton's second law in terms of momentum. F net is change in momentum over change in time. Now, time is a scalar. Time has no direction, so it's not important, okay? That means we have to consider this vector and that vector. Because F net has, and we've got that equal sign, these directions have to be the same. So the direction of my F net will be the direction of my change in momentum. So if F net is to the right, change in momentum is to the right, regardless of the direction that the object's moving in. And this all sounds quite weird at the moment. Don't worry, we're going to break it down a little bit further later on. If change in momentum is upwards, then the net force must have been upwards. If the net force is backwards, then the change in momentum is backwards. So whatever direction the net force is in, the change in momentum is the same, okay? They go together. Net force, the direction of net force is the same as the direction of the acceleration as well. We spent a lot of time on that last time, okay? So, I need you, because we're going to go for a short break, just to try and get your head around F net direction equal to change in momentum direction, okay? And then we'll work through it in the next section. So I'll see you in a couple of minutes. Welcome back. I hope you're ready to continue with our discussion of change in momentum, okay, because you know that's what we're working on at the moment. So, how do we calculate change in momentum? Because we've spoken about it, what we would call qualitatively, okay, so we've looked at it in words and explanations, but really as scientists, we want to do calculations, especially physicists, okay, when we're doing physics. We like numbers. We want to do a calculation because the numbers make sense. Well, they should make sense, okay? So how do we calculate change in momentum? There's a couple of ways we can do it, and we're going to break it down to the way that makes most sense, and it's all about the change in velocity. So, first of all, there's my equation. Change in, delta means change in, momentum is final momentum minus initial momentum. Whenever you do a change in something, and this goes across your science, if you're going to work out the change in something, it's always final minus initial. It's okay to get negative numbers, okay? So, delta P means change in momentum. It's still measured in kilogram meters per second. Just because it's changing something doesn't mean its units will change. PF, F stands for final, so that's final momentum. PI is initial momentum. Now we know that more than likely we're not going to be given an equation where they give us the value of the final and initial momentums. We will have to work those out. So I can change the equation to be mass times V final minus mass times V initial. Final velocity will give me final momentum. Initial velocity will give me initial momentum. So M is mass in kilograms, that hasn't changed. VF, final velocity, you should recognize that from equations of motion. VI is initial velocity, also recognizing it from equations of motion. But remember, mass is constant. We're going to, like I've said before, we're working with situations where mass is a constant. So we can take M out as a constant value. And what's not there, so you'll see now, so if I take M out, we end up with VF minus VI, and that little expression means change in velocity, okay? Okay, I didn't put that. That gives us change in velocity. You are not given this equation, okay? This is not going to be on your information sheet. But it's easy to work it out because I want change in, final minus initial, okay? Obviously, if you learn the equation, it's going to make your life a lot easier, but it's not a difficult one to remember. So, here is where life gets fun for us because change in momentum is a vector, which means it has direction, which you know. So, how do we show change in momentum in a vector diagram? Now we need to be careful. If I'm just considering a value, so I tell you that the change in momentum is a certain value, that's easy. I can just go, there we go, so say we told you it was 6 kilogram meters per second, and we're going to say it's going to the right. That's easy enough, but here, often what they'll do is they'll say to you that you have an initial momentum, you have a final momentum, and then they want the change in momentum and you have to put it on a vector diagram. Here it gets interesting, okay? So I'm going to say we have an initial momentum. I'm not going to worry about the size of it right now, okay? That's moving to the right. then the object changes momentum. Now, unlike normal vector diagrams, where you would add the vectors together, so you would go head to tail, and normally, so this is my initial momentum, okay, and say it speeds up, okay, we would normally go, well, there's my second momentum, okay, P final. We can't do that with momentum because it's not a force. If I now drew, because now if we had said what was the resultant momentum, we would draw something like that. This doesn't work because this is P, oopsie, I didn't want to do that. This is PF plus PI. We've added the two together. But changing momentum needs to be a minus, okay? So we can't do that. What we do is this. Let's take those away. When we draw it, we draw both momentums from the same starting point. So there's my initial, there's my final. That's P final. Now the change in momentum, okay, always goes from the end of the first momentum to the end of the second momentum. In other words, oops, no, let's use that one. It goes from the end of the first one to the end of the last one. That represents the change in momentum. And I can get that value by going PF minus PI. It's the difference between them. So that's the biggest difference to what you would normally do with vector diagrams, okay? Because change in is not resultant. It's not the addition of the two vectors. It's the subtraction of the two vectors. We are going to do some more examples, and that's the one that's a little hard to get our heads around, okay? But we are going to do more, so don't worry about it. Because how these velocities change gives us a way to predict whether we're going to have a big change in momentum or a little change in momentum. It all depends on the situation, okay? So, that brings us to the end of this section, which was quite short, but it's okay. We're thinking about the vectors of changing momentum. We've got the equation now. In the next part, we're going to do the calculations. So I'll see you in a couple of minutes. Welcome back, everyone. Last section, last push for this. We're going to do some calculations, and hopefully, because I think there are probably some questions still about the direction in change in momentum, hopefully that'll get sorted out as we go along. Okay, so let's just hop in there. So what we have is this. A soccer ball with a mass of 425 grams, that's the average mass of a soccer ball, is moving at 2 meters per second to the right. A soccer player kicks the ball so that its velocity is now 3 meters per second to the right. They ask you to calculate the ball's change in momentum. So, what I suggest, draw a diagram, okay? This isn't a particularly difficult situation to understand, but we all think better when we can visualize it, okay? Now we know I can't draw, so we're just going to go with it. So what we have is we have the foot of the soccer player. Here's my ball, okay? The ball has a mass of 425 grams. It's initially moving at 2 meters per second. Then the soccer player kicks the ball. There we go. So here's his leg again, which has changed size and shape, but we're not going to worry about that. And now the soccer ball is still going to the right, and it's going at 3 meters per second. They want the change in momentum. They're not looking for force, they're not looking for any of those, they want change in momentum. So we know change in momentum would be final minus initial. You absolutely can do this question so that you first work out the final momentum, you work out the initial momentum, and then you minus the two. You're more than welcome to. But remember, we can do this equation, which you've seen, to look like this, where we take mass and we take final velocity minus initial velocity. That's the way I'm going to do it. The reason why I do it this way is I'm doing less equations. I'm less likely to make a mistake that gets carried down, okay? Because it's easy to make mistakes. We all do them. So we want to try and avoid it, okay? And I wouldn't say this with every section, but with this one in particular, trying to keep it all in one equation is a good idea. Now, the mass of my object is 425 grams. Remember, we can't work in grams, so we have to change that to kilograms, which means we're going to divide by 1,000. Just quickly, your information sheet always says round off your final answers to at least two decimal places. That doesn't include conversions, okay? So I can't convert this and now round this off to 0.43 because it's not 430 grams. When I convert this, I have to keep all the decimals. All right, that is not an option here. Please be careful because if you change it to 0.43 kilograms, they're going to mark your substitution wrong, which means you don't get the final answer right either. So be careful. Let's substitute in what I know, okay? So I've got 0.425. Final velocity was 3. Initial velocity was 2. Okay, I'm going to do it on my calculator because it's important that we know. So what have we got? Okay, we've got 0.425 times, there's my bracket, 3 minus 2. Not allowed to have a fraction, must convert it. Oh, look, 0.425. So we get a positive answer of 0.425 kilogram meters per second. Now, what I haven't done is said what a positive answer means because we just went ahead and did it. What we have done by default, without even thinking about it, is we've made to the right our positive direction because none of these are negative. We've left them as positive. Be careful here because this was done by default. You need to think about how that happened, okay? We have to always allocate a direction as positive when we do calculations like this with vectors. I would have, if I'd actually thought about it at the beginning, gone to the right as positive. My default, in other words, what I do naturally when I look at calculations that require a direction, is I make original direction of motion positive. That doesn't mean that I'll always get a positive answer at the end or I'll always get a negative answer at the end. It just means that every time I look at a question, I'm starting from the same point. So it's one less thing for me to think about before I get going because it's just a natural. Original direction positive, which means here original direction is positive. I got a positive answer at the end, which means that is to the right. Okay? Straightforward. Now for the fun part. Draw a vector diagram representing the change in momentum. What we're actually going to do is I want to show the initial momentum, I'm going to show the final momentum, and then I'm going to show you where the change was. Okay? We didn't work out the values of the initial and the final momentum. We don't need it. Okay? Final velocity was bigger than initial velocity, which means final momentum is going to be bigger. I'm just going to draw it as a bigger line. Okay, so initial momentum is going to the right. final momentum is going to the right. Now, change in momentum always goes from the end of the initial to the end of the final. There's my change in momentum. And it's tiny because we knew that that was 0,425. It's tiny, okay? So we've got the initial and the final, and then we've got the change. So remember, the initial and final momentums must start at the same place. Little different to what we're used to when it comes to vector diagrams. Okay. Now, same soccer ball. Moving at 2 meters per second to the right. Now the goalkeeper catches it and the ball stops. Final velocity is 0. Then they ask, what is the ball's change in momentum? We have to have a direction as positive, which is going to be to the right. Now we've got to say to ourselves, are we expecting a bigger change in momentum than before or a smaller change in momentum? And here, the more you do this, the more you'll realize how this is going to work. In the first question, it went from 2 meters per second to 3 meters per second. Its velocity only changed by 1. Now it's going from 2 meters per second to 0. The velocity is changing by 2. That implies for me that the change in momentum must be bigger. That's what my head is telling me, okay? Let's see if that's the case. So, we could draw a diagram, but I think this one's easy to understand. So we're going to do change in momentum. This time I'm going to start by saying that it's m delta v. It's one of the equations. We know we can use it as it is. Okay, again, if you want to go calculate the final momentum, calculate the initial momentum, minus them from each other, you're welcome to do that. Okay, so my mass, because we worked it out last time, 0,425. Final velocity is 0. Initial velocity is 2. I'm hoping some of you are looking at this and going, hang on, wait. We're going to get a negative answer. Yes, we are. Now I want you to think about whether that makes sense. We'll talk about it. So, in other words, my calculation, 0.425 is 0 minus 2. Okay, we can't use the fraction, so we get negative 0,85. Number one, it's bigger than the last one we did. We expected that. Number two, it's negative. That means that the change in momentum is to the left, because our answer is negative and the positive direction is to the right. So this becomes 0,85 kilograms meters per second to the left. Now, we've done Newton's second law in terms of momentum. We also said that the net force would be in the same direction as the change in momentum. That means the net force that's acting on my ball must be to the left, which makes sense. The ball is going to the right. The goalkeeper catches the ball. So the goalkeeper must be exerting a force to the left to get it to stop. If the goalkeeper is pushing the ball to the right, I was going to get there eventually, the ball's not going to stop. It's going to go in the goal, and then no one's going to be happy, okay? So the goalkeeper has to be in the opposite direction to the motion of the ball so that it will stop, okay? We expected a bigger change in momentum because there was a bigger change in the velocity. That one was fairly straightforward to get. If we now look at the diagrams, all right, I'm going to do all three again. Initial momentum, okay. Final momentum, nothing. Okay, didn't go anywhere. I can't draw a diagram, it's 0. Now, change in momentum has to go from the start of the first one, oopsie, to the end of the first one to the end of the last one. It goes backwards. And in fact, the change in momentum would have been the same as the initial momentum. It's just in the opposite direction. So it goes backwards. The thing here is where it starts. That's the big thing. Okay? That one's not so bad. But what if the ball changes direction? So we've done same direction speeding up. We've done same direction slowing down, essentially, or stopping. Now what happens if the ball changes direction? So, same ball, same initial velocity. So I'm still going to take to the right as positive. But now a soccer player comes along, because he's trying to get a goal. Now we're not going to let it go to the goalie. And he kicks the ball so that its velocity is now 3 meters per second to the left. The ball has changed direction. Now we've got to think about it and go, well, are we going to get a big change in momentum or a small change in momentum? I'm actually not going to tell you. Okay, I want you to look at the value. So we've got a 2 and a 3, but there's a change in direction. So actually, we've gone from plus 2 meters per second to minus 3. Think about that in terms of a number line, because we're actually looking at how many spaces on the number line there would be. So we've got to go, yeah, I'm going to let you think about that. Let's see what we get to at the end. So, we want change in momentum. Change in momentum is m delta v. The mass hasn't changed. It's been wonderful. So it's 0,425. Final velocity was minus. So it's minus 3, minus 2. Hopefully, some of you are going, hang on, wait. We're going to get a negative change in momentum. Is that going to make sense? Well, let's see. Okay, so calculator, 0,425 minus 3 minus 2, close our back bracket, fraction again, minus 2,125. So that means that my change in momentum is to the left. Let's think about that. The ball came along, soccer player kicks the ball so it changes direction. The change in momentum must be in the opposite direction. The net force on the ball must be in the opposite direction or the ball's not going to change direction. So I'm okay with that. But it's a big change in momentum. It's the biggest one we've done so far. Why? Because of the change in direction. So this makes this 2,125 kilogram meters per second left. Okay? Guess what we're going to do? Because we've done it lots today. We're going to draw the diagrams. So, initial momentum. Now watch what happens. My final momentum is in the opposite direction, but remember, we start from the same place. Now my change in momentum goes from the end of the first one to, stop it, to, there we go, I'll draw it all nice for you, to the end of the last one. There's my change in momentum. And it's a much longer line. Okay, change in momentum is related to the net force. So in your head, when you do these calculations and you get to the final answer, you've got to say to yourself, does it make sense with the direction? How did the force applied interact with the object to get the change? Then it'll make sense to us. Then we can picture it. Then we can go, okay, that makes sense. I can work with that. Okay? So, what does the size of the change in momentum tell you? Well, it tells you about the net force. It tells you whether it's a big change in momentum or a small change in momentum. It can also tell you whether it changed direction. Okay? So the size does mean something for us. When there is a change in direction, there's always a big change in momentum, okay? So there we go. What I'm trying to get to with this is you saw, so with the first equation, it went from 2 meters per second to 3 meters per second, but it was in the same direction. So it was a small change in momentum, and it was a positive change in momentum. When it went from 2 meters per second to -3 meters per second, velocity magnitudes are the same, but because we changed direction, big change in momentum, okay? That also means that for it to change direction, we needed to apply a bigger force. Net force is directly proportional to the change in momentum. So if I want a big change in momentum, I have to apply a big force. If I want a small change in momentum, and I have to apply a small force. But what I need you to remember here, and this is important, when there's a change in momentum, we always get a maximum change in momentum when there is a change in direction. Okay, so when you look at a problem and you see that it's something like a ball being hit by a tennis racket, okay, it's going to change direction. The hockey stick that we've done before changes direction. Cars are a little different because, of course, we could be going forward and slow down, forward and speed up, but it's still part of that, okay? So that whole change in momentum is related to F net. Same direction. When we get onto collisions, which we're going to do in the next lesson, that becomes quite important, okay? And when we get to impulse near the end, that F net being in the same direction as change in momentum, vitally important for us to get, okay? Very, very, very important. So, what have we done? When the velocity of an object changes, the momentum of the object changes. Change in momentum and net force are in the same direction. No, I'm making a big deal out of it because it's important. Change in momentum can also be represented by a vector diagram. And that one you maybe have to go through again. So, that's the end for today. So we've done a lot, okay, which you need to keep in your mind. Next time, we're going to look at collisions and explosions. It's very exciting, okay? But until then, think about what we've gone through, go and revise it. I promise you, you can get this. But I'll see you next time.